exam. I mean, this section is not covered in the final exam and your assignment and your short test. Okay, so only for your knowledge, I will explain this part. Let me share my screen. Okay, we have vibrations condition monitoring, and in this slide I will use an example from a bearing vibrations, a specific bearing, and I will show you how to do this monitoring and how to do the analysis. Generally, we use the vibration monitoring and use the, in fact, the experimental test for the vibration for two main purposes. The first purpose is to extract the characteristic of a system. For example, we use the accelerometers, or we use the modal test to extract the first natural frequency of a system, and also the damping ratio in your structure. But most of the time in industry, we use the vibration test to in conditions monitoring, based conditions monitoring the system, the structure. For example, in the industry, assume that you deal with a machine. This machine will have some vibrations, and if you monitor the vibration of this machine for a specific period of time, you can monitor the health of your machine. You can monitor the behavior of your machine. If some of this parts, some of the components in this machine will have some problems, some issues, you can see and you can monitor this behavior in the vibration monitoring test, and you can see this behavior in the condition monitoring by using the accelerometers or other equipment in vibration test. So here in this slide, I want to introduce you how to do the vibration monitoring. First of all, we will discuss what can we do with the data extracted from the accelerometers. We will have some data from a bearing vibration, and then we will discuss the time domain analysis. Later, we will have the frequency domain analysis, and finally, I will tell you how to calculate on your own and extract this data, and how to use this data to extract this analysis, time domain and frequency domain. And finally, we will have the conclusions. So as I told you, this data in this part is related for a bearing vibration in a specific machine that you can have access to the data which are collected on this link. There are a lot of different data for different bearings. Most of our focus is on the normal bearing and the bearing with the fault 007 in this slide. And I will show you that what we'll do with this data. If you go through to the website, on that link, you can see this type of information. You can see, for example, you have a drive and inner raceway with 007 diameter fault. The depth is 011 and the brand of the bearing is SKF. So if you click on each of this data, you can download the data and you can do your analysis for yourself. But this data will be collected by using the accelerometers. And at the end of this slide, I will tell you that how you can collect this data yourself by using an accelerometer. So here you can see data which are extracted from an accelerometer. This data, the green one is for the fault 007 and the normal one is the orange diagrams. This is for 10 seconds. As you can see, in 10 seconds, we have a lot of data and a vast and a huge information in this period of time, only in 10 seconds. And this is the acceleration, as you see. And the sensor that they use to extract the results and extract the data, in fact, the unit of this sensor is in G. Of course, you can convert it by using the softwares or by using the different coding in different softwares. You can convert it into meter per second square or any other unit. But usually the data which are extracted from the accelerometers are usually in G. For example, here you can see 0.2. It means that 0.2 times by G is the acceleration of your system, of your structure. And this fault is 007. If you want to know that, what does it mean? It means that, in fact, when we have, for example, fault 007, it means we have a fan with end bearing with fault in the inner race measuring in 007 inch in diameter, of course. So we have different data, but here we focus on these two types, the normal and fault 007. And all of these data are collected when the machine, in fact, because these data are collected from a electrical motor, when this motor is running at approximately 1772 RPM. Here in this graph, you can see that we zoom in for a specific 0.25 second period of time from 3.75 to 4 seconds. And you can see some points. We have some big points for the acceleration. For example, in these points, we have peak, or here we have a negative peak. These points are important, and we will discuss that what we can do with these results. At the first, when you look at these results, you cannot extract any conclusion, but by using the vibration analysis, you can extract some results and you can monitor the behavior of your system. So first of all, we start with the time domain analysis. And in the time domain analysis, we will extract some characteristic in our diagrams. For example, we can extract the acceleration peak, the RMS for acceleration or velocity or displacement. For all of them, we can extract the RMS in time domain. We will have the crest factor, we have the standard deviation, and also we can integrate the acceleration to extract the velocity and displacement. You know that from the acceleration, by integrating the acceleration, you can extract the velocity and displacement. The velocity is the integral of the acceleration and displacement is the integral of velocity. So by double integrating the acceleration, you can extract the position of your system or the displacement. But you will see that most of the time we cannot directly find the displacement in time domain, of course, from the acceleration, because there are a lot of nodes and we need some corrections to extract a modified displacement diagram for the system. And another point that we usually use this analysis, the time domain analysis, to condition-based monitoring of the system. In fact, when you want in the industry, assume that, for example, if you want to work in a factory and you want to monitor the behavior of a specific machine, you need to collect the data in a specific period of time. And then you can do this analysis that I will explain in time domain to condition-based maintenance purpose. So you can use the time domain analysis for the condition-based monitoring of the behavior of the system. But if you want to extract the characteristic of your system, we usually prefer to use the frequency domain, and we can extract the different characteristics such as the natural frequency in the frequency domain. But in time domain, we can monitor and we can track the behavior of different components in the structure. And by seeing the difference in the behavior, we can find out that there are some problems in the components. Okay, first of all, we start with the peak acceleration. As you saw, there are a lot of peak in the acceleration diagram. We can find the peak. Of course, we should find the absolute values of the data, the peak for the absolute value, because we have some peak points which are negative, and if you only consider the peak for the values of the data, you will miss the negative peak points, and sometimes the negative peak points are more important than the positive point one, because negative and positive is only a direction of the acceleration. So we should consider all of the uh, peak points on your acceleration, and easily you can write a code to extract the peak points, but there are a lot of software that you can do this analysis. Here you can see it. We have three different diagram for the sine function. We have in this graph, in fact, we want to compare the effect of the sample rates, especially when you want to extract the peak point for the system. Assume that we have different sample frequency. The sample frequency, it means that, for example, by increasing the sample frequency, you are increasing the number of the points that you are recording the data. For example, the blue line is the 100 hertz, and when we have 100 hertz, it means that at each second we record 100 times the data. But when we have a 29 hertz, it means that at each second 29 times we record the data, and finally for the last one, which is 15 hertz, we only record 15 times in 1 second. So if you can compare, you can see, for example, for the frequency 15 hertz, when we are before the 0.2 seconds, we missed a lot of data. Here you can see, for example, we missed this data when we use the 15 hertz sample frequency. And also here, we are missing this data, and these peak points are missed, or here we are missing this data. So when you want to do the peak acceleration analysis and you want to obtain the acceleration peak in your diagram, in your data, it's very important to consider the sample frequency. Of course, definitely by increasing the sample frequency, you can increase the accuracy of your calculations. But by increasing the sample frequency, the volume of the calculation will be increased, and definitely your software or your code need more time to extract the results, to do the analysis. Here, if you look at after 0.2 seconds, we can achieve to the peak point. I mean, we almost achieved to the maximum value of the result, but still we missed some data. So it's very important to find an optimum sample frequency. For example, here you can see that 29 hertz is almost good. So if you want to do the analysis with this frequency, with this sample frequency, you will have a good and an acceptable accuracy, but still we can miss some data which according to our application, it maybe it's not very important. So the sample frequency is very important, and we should consider in our time domain analysis. The next one is the RMS. The RMS, you can calculate the RMS for the acceleration, velocity, and also for the displacement. but we usually use the RMS in acceleration and velocity only. In the acceleration, you can see, you can use this formula. We have the data. So by substituting into this equation, you can calculate the RMS of your data, and you can calculate this value, which is in fact the root of the square root of the mean of squares. Here you can see this AI is the acceleration at each second, and we have n data according to the frequency of the sample frequency. This n will be increased or decreased, so we will have n data for a period of time. So by substituting into this data, into this formula, you can calculate the RMS for your acceleration. But if you want to calculate the RMS of the velocity RMS, it will be an important parameter, because the velocity RMS is usually related to the energy of the system. And in the vibration health monitoring, we usually use the velocity and acceleration RMS, which they are very important data, and we need them. Another parameter is the crest factor, which is the ratio of the peak acceleration to the RMS acceleration. So in fact, it is a dimensionless parameter, and it can show that how peaky is the acceleration or your signal, how peaky is your signal, and you can study again for the vibration health monitoring, you can study this parameter. And this behavior is very important. I mean, for example, you have 2 or 3 different signals for a specific machine in different period of time. And if you compare it and compare the crest factor, you can monitor the vibration, you can monitor the health of your structure and the components. And the next one is the standard deviation. The standard deviation, in fact, is similar to the RMS. In fact, to extract the standard deviation, first we need to take out the DC offset of our signal, and then again we can calculate the RMS. So this is similar to the RMS, but we do not consider the DC offset of our signal. Here you can see some data. For example, for the bearing vibration data, we have, this is the acceleration peak. Of course, in this table, we have the fault 0 to 1 and fault 0, 14, in addition to the fault 0, 0, 7 and the normal. We have the acceleration peak. If you compare, you can see in the normal bearing, the peak acceleration is 0.269, and it will significantly increase when we have fault in the system. So by checking this parameter, you can check the health of your system and monitor the behavior. Or here in the acceleration RMS, again, you can see from normal to fault 007, we have a huge or a significant jump in the acceleration RMS. In the crest factor, we have the same. Again, if you calculate the crest factor and compare for different signals, you can see the effect of the fault, especially from normal to fault 014. We have a huge jump. It's almost 2 times more than the normal one. And finally, the standard deviation. Again, in the standard deviation, you can see that the standard deviation is almost, for the fault 007, it's almost 2 times more than the normal one. So by using this data, you can extract the data from your machine, from your system, your structure, and compare, and you will see if you have a huge difference between the data, definitely you will have some fault in your structure, and you can find the fault before that you will have any catastrophic failure in your structure in your machine. Okay, so before that you can change that component. For example, if you deal with a bearings, you will have some diagrams and some tables like this, and when you record that your, for example, acceleration peak was 0.269 in, for example, January 1st, you record this data, but after 2 months, for example, in March, you again record this data and this acceleration peak for your system. So you can conclude that definitely there are some fault in your bearing, and your bearing needs to be changed because we have some fault and we have some difference in the data, in the recorded data. But here, for the pure sinusoidal signal, again, we extract the results. You can see we have acceleration peak for the signal with 100 hertz and without any bias or without any DC offset. 20 hertz. Of course, this is the sample frequency, 100 hertz, 29 hertz, 29 hertz with 1G bias or 1G DC offset, and finally the 15 hertz, the signals that we had in the previous slide. If you extract, the acceleration peak for all of them is almost the same. I mean, for the frequency with 100 hertz, you can see this is the acceleration peak. For the 29 hertz, it's almost the same. And for the 15 hertz, it's 0.995. And again, it's with an acceptable error, it's good. And for the 29 hertz with 1G bias, we have one shift by 1G because we have a DC offset of 1G. The acceleration RMS, if you compare them, you can see the acceleration RMS is for the 100 hertz and 29 hertz is almost the same. But for the 29 hertz with 1G bias, again, it will be different because we have a DC offset. But if you compare the standard deviation for all of them, you can see they are the same because there is no offset. And in fact, this 1G offset in the 29 hertz 1G bias will be take out, and then the RMS is calculated. And finally, the crest factor, you can see for all of them is almost the same, but for the, when we have a 1G bias, we have a different result. So it's better always to take out the DC offset or the bias and then do the analysis for the data. Okay, as I told you, the last application of this data in the time domain is to calculate the velocity and displacement by integrating the acceleration. So we can find the velocity by integrating the acceleration, and also by integrating the velocity, we can find the displacement. Also, of course, we can use this method in the frequency domain to extract the velocity and displacement in frequency domain. But in the time domain, there is a problem, and most of the time when you calculate the velocity and displacement, since there are a lot of noise in the real world, and when you record the data, definitely you will record some noises from the environment of your system. So when you calculate the integral, definitely we will have an error in the velocity, and especially when you calculate the displacement, because you will have double integration, and 2 times you should calculate the integral. So your error will be more than the velocity, and we need some methods. For example, we can use the filters to vanish these noises. So to calculate the integral, you can use different methods. Usually for a specific sensors, there are some specific softwares. I mean, when you buy a specific sensor, there are some softwares that you can buy the software at the same time. This software will help you to calculate the velocity and to calculate the displacement, and you can do all of this analysis in fact by this software. And if you want, you can write a mathematical code in any software. For example, in Maple or MATLAB, Mathematic, or any other software you can write, and you can write a code, and then you can calculate your time domain analysis. But you should remember that when you want to calculate the integral, you should consider some modification on the integration, because we have some noise, and for this purpose you can use a band pass filter or low frequency filter, and also you can use a taper, which taper means that taper will force your data to start and end at 0. But usually, as I told you, these codes are usually are prepared in and provided in different softwares for the sensors, and you can use them directly. For example, here you can see we have two different signals. The first signal is a pure sinusoidal signal, and the red one is a signal with some noises. And usually when you collect the data, when you record the data in your accelerometer or in your sensor, usually we have these noises from the environment, and they will record with your data. And when you want to do the analysis, you should consider this noise in your analysis. So here, if we want to do calculate the integral and find the acceleration and velocity for this system, here you can see the results. The blue one is the pure sinusoidal signal that we calculate the velocity without any modification. You can see that we have one offset for the signal without noise. But when you use the taper, or when you use the filters and taper together, you can see that the results are completely correct. Here for the green one and orange signal, you can see in this area. And if you compare with the exact value for the sinusoidal signal, you can see that by using the taper and filter, we can achieve an exact value for the velocity and displacement as well. But when we have noise, you can see the red one is the original signal that we directly calculate its integral. You can see we have a lot of errors, especially here we achieved about 30 inch per second, but despite the value, the real value is less than 10. For the purple one, which is the noise with a taper, we modified this, but still we have some errors. But when we use the filter and taper at the same time, you can see that the results are modified and the results are acceptable. And the maximum is about 10, and this is acceptable. For the displacement, you can see again when we do the integration, again for the signal without noise, again when we directly calculate the displacement from the acceleration, you can see that results are not correct. But when we use the taper, or when we use the taper and filter together, you can see that the results are correct. Again, for the signal with noise, the red one is calculated without any modification, and only by double integration from the acceleration. This is completely incorrect. The purple one, we have used only the taper. The results you can see, especially in this period of times, are not correct. And finally, for the last one, which is blue, we are using the filter and taper, and the results are completely correct. So you can see it is crucial to use the taper and the filter in the integration. And of course, I should again mention that if you are using a specific software, usually the softwares will use the filters and use the tapers, and they will modify your signal. Again, if we back to the results and the data for the bearing, you can see this is the velocity and displacement, which are calculated by using the taper and filter, the displacement and the velocity. But there is an important point here. When you compare the purple one, which is the normal one, you will see we have some peak in the displacement and also in the velocity. I mean, when you calculate the integral for two different signals, despite the green one is the fault 007 in the acceleration diagram, in the acceleration signal, we had all of the peaks are related to the fault signal, but here in the velocity and displacement, you can see that the peaks are related to the normal signal, and the peaks of the fault signal are negligible in comparison with the normal signal. The reason is because later in the frequency analysis, you will see that because there are a lot of low frequency in the normal one, and in fact, the frequency of the normal one is significantly less than the fault bearings. Here you can see that these signals and these frequencies are dominant, and we have some peaks. So again, if you compare these graphs, you can find out if there is any fault in your structure. Yeah, this is the explanation that, as I told you, the normal bearing displayed quite a bit higher velocity and displacement level. The reason is when integrating data, the lower frequencies dominate the resulting integration. And we'll see in the next section that, as I told you, in the frequency analysis, you will see that the normal one has lower frequency in comparison with the fault signal. Here you can see the RMS velocity and RMS displacement for different signals. The normal one, you can see significantly the RMS of the velocity is higher than the other fault, and also the displacement RMS for the normal one is higher than the fault signals. Again, this is another parameter and you can use it, another criteria to obtain the fault in your components. As you can see, by decreasing the RMS in the velocity, in fact, the energy in your system will decrease. Okay, and here, this is the importance of the velocity and displacement RMS. As I told you, because the velocity corresponds to the energy of the system, this tends to be the primary metric tracked over time for vibration health monitoring, for condition-based and predictive maintenance. And for the displacement RMS in the most of the mechanical systems, large displacements only occur at very low frequencies. This is related to the resonance phenomenon. I mean, when you have the data and when you do the time domain analysis, you can see that we have a very huge, for example, peak in your displacement, and especially in your displacement RMS, you will see that you have a huge um value and a huge jump. So it can be due to the resonance, and maybe the frequency of the excitation is close to you to the frequency of your system, or maybe your system is changing and its frequency has been changed, and it's getting close to the frequency of the excitation. So it can be another important parameter that you can check in the time domain analysis. But about the velocity, sometimes maybe you ask that how do we obtain what low or high is in the velocity. For your system, you can use the different standards. Here, for example, we have an ISO standard that is called 10816. According to this standard, of course, we have different classes for the machines, and the dimension of the machines can obtain the class of your system. And according to the dimension of your machine and the class of your machine, you will see we will have different value for the velocity. So if you record the velocity RMS, you can compare with this standard, and you can find out that the velocity of your system is acceptable or not. For example, if you calculate that the RMS of the velocity is, for example, 4.5, and your machine is in class 3, it's satisfactory because it's located here. But if your class of your machine is 2 or 1, it's unsatisfactory. And by increasing the RMS of the velocity, or and the velocity RMS, you will may shift to the unacceptable velocity. So you can compare and you can monitor the behavior of your structure, and you can do if it is required to do any modification on your structure. Okay, this is the frequency domain analysis, and we can do it maybe tomorrow, because for today it's enough, and tomorrow we can finish these slides. Okay, any question from this part? No questions? Okay, thank you. And for the final exam, we will have several multiple choice question. We will have several problem-based question and one design question. In the design question, you should consider some initial value for your system and design a vibrating system. Only maybe the design problem will be a little different from the examples during the lectures that I've solved for you. For that case, you should assume some value for example, in your system for the spring stiffness, and then you should solve the problem. Okay, we will have 3 different types questions. Okay, any other question? Okay, thank you for your attention, and we can continue again tomorrow, and bye.